Thank you so much for the incredibly kind introduction. And I mean, it's workshops like these where it brings together lots of different people where I get so excited about hearing about different ideas and working and bridging these boundaries or whatever. So as you'll see, the work that we're doing is really this huge, massive collaboration. And it's a little bit different probably than what you're used to hearing about. But I hope that there are some pieces of ideas there that might be useful for some of your own work as well. So yeah, today I'm going to talk about the first portrait of our Milky Way's black hole and what we're going to next. So what do I mean by that? So if you go out past the bright city lights, you might be lucky enough to see this stunning view of the Milky Way galaxy. And if you could travel past millions of stars to the heart of our own Milky Way, you would eventually reach this cluster of stars right at the center. And by peering past all the galactic dust with infrared telescopes, astronomers have mapped this cluster of stars over decades, and what they see is quite remarkable. As the stars come close to the center, they get whipped around by this massive but unseen object just sitting there. And by tracking the stars over time, astronomers have concluded that laying within the orbit of these stars has to be a massive compact object with the mass equivalent to 4 million of our suns. And in fact, this discovery led to the Nobel Prize in Physics in 2020 for the work of Andrea Ghez, UCLA's very own Andrea Ghez of the Galactic Center Group here, and Reinhard Genzel for the discovery of a supermassive compact object at the heart of at the center of our galaxy. And for many years, people have believed that this compact object is likely a black hole, an object so dense that its gravitational pull is going to suck up anything that ventures too close, even light. But at the distance that these stars are orbiting, you actually can't stay for sure. And so in order to study the black hole, we really have to zoom in 1,000 times closer. And there, Einstein's theory of general relativity makes some really exciting predictions for what we should see. So light propagating near a black hole doesn't follow straight lines. It's curved because the black hole is actually curving space-time. And so if this was a black hole, the space around it would be lit up by this hot gas. It's heated to hundreds of billions of degrees, and you have photons flying around everywhere. Some of them fall into the black hole, but other ones just graze it and are bent by its gravitational pull. So that the net effect is essentially the black hole casts what we call a shadow on the backdrop of hot emission that's almost perfectly circular. So we don't see the black hole. We wouldn't expect to see the black hole itself, but instead the imprint of the black hole, which we call the black hole shadow. But this ring doesn't take on just any kind of size and shape. If Einstein was right about general relativity, the size and shape would be directly related to the mass and the spin of the underlying black hole. And so if astronomers were right about that, 4 million solar compact object at the center of our galaxy being a black hole, then we would expect to see a ring of about 50 microarc seconds with not a lot of wiggle room for us to play with there. And so after many decades of studying this mysterious object, just back in May, we revealed the first image of this massive body, which is an image that lined up perfectly with prior observations and theory. And so this is the first ever picture of the black hole in the heart of our own Milky Way galaxy, a radio source called Sagittarius A star, or we like to call it Sag-A star for short. And taking this picture, as you'll learn, took this Earth-sized telescope and an Earth-sized team. But what makes taking it so difficult? Well, the fundamental challenge is one of scale. Because the black hole is so massive, it occupies an area about as big as Mercury's orbit around the sun. And that might sound large, but at 27,000 light years away, this is like trying to take a single photograph of a grain of sand, but if that grain of sand is in New York and we're viewing it from where we are here in UCLA. And so taking a picture of something that small required this international collaboration of scientists from all around the world building new instruments and algorithms to make it possible. And so today I want to tell you a very abridged story of how we were able to take a picture of this black hole. But at this point, you may be saying to yourself, wait, am I feeling a bit of deja vu here? Did I hear this story before or see a picture like this before? And if I turn this image around, it might look like another image that you may have seen a couple years back. And this here is the first image of a black hole ever produced, which our same collaboration published back in 2019. But this image of the black hole here is not the one in our Milky Way galaxy, but one at a galaxy that's 55 million light years away from us called M87. And you might think Sagittarius and M87 here look eerily similar, but that's actually no coincidence. That's actually predicted from Einstein's theory. But as I said, we published this image of Sagittarius just back in May of this year, and M87 was published back in 2019. Yet these images were recovered actually from data that was collected in the exact same week of 2017. So today I hope not just to answer how did we image M87 and Sagittarius, and in that you'll see that there's some interesting connections with phase retrieval that we have to deal with, but also I want to tell you along the way what made Sagittarius so much more challenging. And as we're learning about this, I hope to also lead into two kind of projects that I want to tell you about, two methods currently being developed in my group at Caltech to push the imaging of black holes past current limits to see things that are still invisible to us. In particular, I'll be talking about uncertainty quantification, machine learning approaches we're developing for imaging, and also recovering a 3D dynamics of a black hole over the course of a night in the future. Okay, so let's get started. So again, why is taking a black hole so difficult? So as you all know from diffraction theory, we can only image things up to certain sizes given certain aperture and wavelength. And so because of the black hole ring is so small and can only be seen at a particular wavelength, diffraction limits require that we build a telescope that's 13 million meters in size in order to see that event horizon scale structure. So 13 million meters is essentially the size of the Earth. And although we obviously couldn't do that, instead the Event Horizon Telescope collaboration spent well over a decade joining telescopes around the world to build a computational telescope the size of the Earth that was capable of resolving structure on the scale of a black hole's event horizon for the first time. And so how does this computational telescope work? Well, the EHT, the Event Horizon Telescope, which we call EHT, doesn't work like a regular telescope. Instead, the radio telescope work in pairs. So unlike in a camera with the Event Horizon Telescope, we don't capture the picture in image space, in pixel space, but instead we're actually going to capture it in its frequency space. So we essentially are going to take measurements of the black hole image's Fourier transform. And if we put telescopes all across the globe, we would sample all these spatial frequency measurements. But because we only have telescopes in a few locations, we only sample a few of these possible measurements. And so it turns out for every 2 telescopes in our telescope array, we sample a single spatial frequency that's related to the projected baseline between the telescopes. But that means that if we have only a small number of telescopes, then we only have a really small number of measurements. Luckily, though, as the Earth rotates, we actually obtain other new measurements. So since the projected baselines between the telescopes change as the Earth rotates, this amounts to carving out these different elliptical paths in the spatial frequency plane. Okay, so how do we make that image after extracting these measurements? Well, at this point, we have the data, and so we can kind of abstract away the astrophysics of the problem and just think of it as a mathematical inverse problem. We have the sparse data, and our challenge is to find the image that caused it. And if we had gotten measurements that covered that entire spatial frequency plane of telescopes all over the globe, we would just simply need to apply an inverse Fourier transform to get back that image. But since we only have a few samples, there are therefore an infinite number of possible images that are perfectly consistent with the data we measure. And on top of that, the fact that there's a different and quickly changing atmosphere above each of the telescopes across the globe causes our data to be really, really noisy. And so I want to explain that a little bit because I think you guys might find that a little bit interesting. So the whole reason that we're able to get these spatial frequency measurements is due to the fact that we use radio interferometry. So light is going to travel from the black hole. Oh, it's kind of corrupted, but hopefully you get the right idea. But light is going to travel from the black hole for, in this case, 27,000 light years, and then it's going to reach Earth, and it'll be at a slightly different time. Oh, it's not running. But okay, there will be a slightly different time delay depending on the location of the Earth. But if you have a different atmosphere, so we have a telescope in Hawaii, and one in Spain, and one in Chile, they all have different atmospheres above them. And so that that time delay originally is the key for extracting that 2D spatial frequency measurement. But when you have a different atmosphere, that introduces an additional propagation delay, which changes the phase of our measurements. And so basically now we have a scrambled phase in our frequency component that we measure. Similarly, the atmosphere can also cause different attenuation factors in the signal, causing a changing absolute gain term as well. And so this error is really challenging because although ideally we would not measure this nice, beautiful Fourier component here, this italicized V, in reality, we have a completely random phase that we have to deal with from the atmosphere. And sometimes we have a pretty bad amplitude as well, although we can usually calibrate the amplitude a little bit better than the phase. But that means that the measurement that we get is nothing like the original Fourier component that we would like to measure from the black hole image. And so that's pretty terrible because at first glance we've lost both our amplitude and phase, so what do you really have left to work with? But luckily, if you look at the measurement term that we have to deal with, actually there's some structure there. So in this measurement term, notice that if we have a third telescope that we introduce, then that measurements that are formed with that third telescope actually share some of the same corrupting terms, G2 and phi2. And so we design algorithms that take advantage of this redundancy of information and basically are trying to solve or eliminate these errors that are site-based because we have all these pairs of telescope information. And so basically it amounts to solving like a constrained phase retrieval problem. But this still doesn't change the fact, even if we put this all in, we still have an infinite number of images that we have to deal with. So how do we recover a single image? Well, to deal with that, we have to introduce preferences for different image statistics into the pipeline. And with this additional kind of information that we kind of inject and to mathematically say what kind of images are better than one another, we can whittle down from infinite possibilities to a single image that fits the data well and is likely under our image model. And so now in a super hand-wavy way, I've told you how you can go from these sparse, noisy measurements to a single image. But note that if we can develop methods such as these to recover a single image, we still have to be super, super cautious. And that's because any imaging method we come up with, whether it's going to require that we inject some additional information into the problem about what images look like to recover something back in the end. And this addition of additional information is always going to bias our final solution. And so we wouldn't want to, for instance, have even a subconscious preference for something like a ring image and then be super excited that we got a ring back in the end. And so I just want to show you this in a little bit in mathematical form. I don't like to put a lot of math, but I just think it will come in a little bit handy later. So we are solving an optimization problem here where we're trying to find the image X that maximizes the posterior probability conditioned on the observed measurements Y. And by just simply rewriting this with Bayes' rule, you can see that we get this term here, the likelihood term, the data likelihood, that says, well, how likely is that data given an image, and then how likely is that image? And so developing methods, so we might be injecting these preferences through this image prior that's here. And so we have to be really, really cautious about this. And so that meant a big question we faced in dealing with the real black hole data was not just how to make an image, but how do we verify that what we're reconstructing with our imaging algorithms is actually real? But actually, nearly everything I've said so far holds true, not just for the Sagittarius star black hole, but also for the M87 black hole that we reconstructed. So before going into how Sagittarius star was imaged, let me do a quick overview of some of the steps we took in the M87 black hole work. And as I said, making an image, we had to be super cautious. And so therefore, we tackled the imaging through a multi-step process, a process that took over 1.5 years to complete, that included many synthetic data tests, blind imaging challenges, and objective learning of imaging parameters. And from this, we learned, as you might expect, no method is perfect. And so it's really important to try to assess the commonalities and differences that you get from different methods when trying to understand, well, what is the true structure up there in the sky? And so with this insight, we didn't just take one method and make a picture, but instead we developed 3 different imaging pipelines, and we designed them to have different hyperparameter knobs on them that control different modeling and optimization choices, like what does it mean to be a good image? What are those statistics of good images? And then typically these hyperparameters or these modeling choices are just tuned by or decided on by a human user. But instead of having a human tune them, we wanted to instead search for the best set of settings to that best recover different kinds of source structures, and then see how that affected the images of the black hole that we got back in the end. So for instance, we generated synthetic data as if the Event Horizon Telescope were actually seeing a disk in the sky that had no hole in the center. And then we figured out, oh, what's the best set of parameters, beta here, that input into our imaging methods that allow us to recover that disk with no hole. And then once we had done this, we transferred these exact parameters onto the M87 data. And although we had tried our hardest to find parameters that would prefer an image with no hole in the center, we found when they were applied to the real M87 data, it required us to put a hole there. And by doing this simple training and testing procedure on just a few different types of underlying sources that we thought could trick us, we saw that our methods always preferred this ring shape. And that was true no matter the day we observed the M87 black hole on or the imaging code that we used to reconstruct it. And so by blurring images from different pipelines to a single resolution, we then averaged them together to form the image that we showed, that we published, and that was kind of shown on the front pages of things back 3 years ago. This ring of light surrounding the black hole, roughly 40 microarcseconds in size and brighter on the bottom than the top. So our goal here was to remove human bias from the final image as much as possible and use very simple training data to select the hyperparameter modeling choices. And by doing this, we got this ring shape, and that was incredibly exciting. But it doesn't answer the question of what is the uncertainty of this image? How likely is that ring, and did we just happen to get lucky? And so how did we do that? Well, previously I talked about selecting one set of parameters here, beta, that performed well on synthetic data, but why should there only be one set? In fact, we found through synthetic data tests that often there was a whole collection of imaging parameters that would do reasonably well. And so rather than just selecting the best set of parameters, we set some threshold and we said, let's find all the types of imaging choices that we could make that performs well in the synthetic data, and then see the collection of images of M87 that would lead to. And so we did this for the different pipelines. So for the EHC imaging pipeline, we had hundreds of thousands of different simulations we did, and about 1,500 of them were chosen to make as acceptable. And then once we had those, we could recover what are the M87 images that would come from those different modeling choices. And here you can see on the left is the mean image, and you see that ring of light. But in the center, we're showing the standard deviation. And so it does show that there are areas along that, around that ring that we do have higher uncertainty in what the exact pixel intensity values are of them. But if you actually look at the standard deviation relative to the mean, so looking at something like the fractional standard deviation, you'll see that that ring was basically in every image that we reconstructed, but what changed from image to image was really all that wispy structure on the outside. So you shouldn't believe any of that you see. But what I want to strongly highlight here is that what we're doing is probing different modeling choices and seeing how that actually affects our results. So in this kind of regularized maximum likelihood problem that I talked about earlier, it's something like changing our prior term, like the image statistics that we might impose, and then seeing how that affected our image that we got out in the end. And this is something that's really important to do, especially when trying to reconstruct an image of something that we've never seen before, right? So we don't know what those image statistics should be. But it's not directly quantifying the uncertainty also due to the data under a fixed prior model. So for instance, as I'm sure you all know with a lot of the problems that you work on, oftentimes the energy landscape that you're actually trying to optimize is super bumpy because you're solving some sort of non-convex optimization problem. And so finding a global maximum can be a real challenge. But even if you find it, who's to say that there's not an equally good solution out there that you've kind of ignored? And so this ends up being a real significant challenge, especially for black hole imaging, where the problem is non-convex and the energy landscape is super bumpy because of this phase retrieval problem that we basically have to solve. So for instance, here on the left side, we have a synthetic image of a black hole. And we took this image and generated synthetic data from it as if the black hole was being seen by, as if the Event Horizon Telescope were seeing this picture in the sky. And so now we have this fake telescope data, and using this mock data set, we ran our algorithms on it and to see what we got. And every time we ran the method with a slightly different initialization, we'd get a different image. In some of the images, the bright spot was recovered in the top right, and in some cases, the bright spot, in this case, was recovered in the bottom left. And so this is a bit scary, right? Because it means that we had to manually explore the space of possibilities. And if this was real data and we didn't do this, we could be missing out on a totally different image that would lead to a completely different scientific interpretation. And so for problems like this, it's so important that we have ways to efficiently visualize the whole space of possibilities, not just recover one that has a really good, score in your loss. And so in other words, instead of computing a point estimate like the regularized maximum likelihood does, we want to be able to sample from a full posterior distribution, the probability of the image X given the measurements Y, in order to visualize that full solution space. And oftentimes, posterior estimation is done using some sort of sampling methods like Markov chain Monte Carlo, but this sampling and rejection method can be prohibitively slow when you're working with high-dimensional imaging problems where you're solving for the value of every pixel in an image. And so to tackle this, we've been developing methods for efficient posterior exploration by exploiting deep learning machinery for the purpose of visualizing the uncertainty. In particular, we aim to learn a deep generative model to approximate the posterior distribution of an imaging inverse problem. And so what do I mean by that? Well, let's start by going back to reviewing some basics of deep generative models, and you'll see why in a minute. So I'm sure many of you are familiar with the great success of deep generative models in computer vision and machine learning in the last number of years. And so what are these generative models? Well, given enough training images, we can train a neural network that takes as input some random noise and outputs from that random noise a picture that looks like a real scene at first glance. And by plugging in different noise images, you'll get different output pictures. So why am I telling you about this? Well, these deep neural networks define an implicit distribution over the space of images. And these impressive results that we've seen in the machine learning and computer vision communities indicate that these networks allow us to learn very flexible and expressive distributions that capture complex correlations in this high-dimensional image space. And so inspired by these generative models, my former postdoc Hassan and I've been developing an approach to sample from a posterior distribution using a learned generative neural network. So our goal here is to learn the weights phi of the neural network such that if you pass different noise, z, into the network, out is going to pop a sample from the image, inverse imaging posterior, the image reconstruction posterior, basically. So you input noise, out comes the sample from your posterior distribution. And different input noise is going to result in different posterior sample images. So essentially, the neural network is just going to be learning a mapping from some simple distribution, this noise distribution, to this complicated posterior distribution here. Okay, so how can we train a network to give us posterior samples? Well, unlike in the case of the bedroom or face generators that you kind of see, we don't have a training set of images to use. If we had a training set, if we had samples from the posterior, we would be done, right? Because there would be no reason to learn a network to give us posterior samples if we already have those samples. Instead, only data we have for optimizing is that sparse and noisy data Y here of a single underlying image. And so in our approach, which we call deep probabilistic imaging, or DPI, instead of using a collection of training images to solve for the neural network, as is typically done in other kind of computer vision problems, we instead found that we can define a loss that is just minimized when the weights of the neural network result in a distribution of network-generated images that best matches the true image posterior. And so in this case, and what I'll talk about is defining that loss in terms of the KL divergence, but there are other kinds of divergences, distribution divergences that you can use that have different kind of advantages or disadvantages. And so doing this, training the weights of that neural network using a loss like this actually ends up being a very specific type of a variational method. So just as a reminder, in variational methods, we define a very simple family of density functions. For example, Q phi here, where every point in this blue ball is actually a full posterior distribution. So it defines each one of those points as a full distribution. And we solve an optimization problem that says, I want to find the parameters phi that best match that target posterior that we're after, the star here. And so typically, so the question then becomes, well, what should that family of variational distributions that we're optimizing over be? And typically, they're usually something fairly simple, like Gaussian distributions or things like this that you can easily compute the integrals you need and all this kind of fun stuff. But in DPI, by using a neural network, we can define a very flexible family of distributions parameterized by phi here, which are the network weights. And this flexible family of distributions can better capture the image posterior distributions we're really interested in targeting. And so actually DPI's optimization problem, so doing this actually, so here I've showed how it can be thought of as a variational inference problem, but also it can also just be intuitively derived by extending that regularized maximum likelihood estimation method that I talked about earlier, because it turns out if you expand this KL divergence here, it turns into just having your likelihood term like we saw before, your prior term like we saw before, but all we add here is this entropy term. And this entropy term basically forces this to not collapse to a single solution, but to find a diversity of solutions that kind of fit the data. All right, so how does this actually work? Well, let's go back to that black hole example that I introduced earlier. So remember, for this ground truth image on top, when we just ran our typical regularized maximum likelihood methods with different initialization, manually searching the space, we saw these different results on the left. But here, we could just train a single neural network from the data that we get here. No different initialization or anything, just train a single neural network. And once it's trained, then you pass different random noise to the network and sample from the generative model. And here are the samples. And you can see that you can get images both with a bright spot in the top right and a bright spot in the top left, similar to what we had seen before. And we didn't have to do any special initialization or tuning or anything. It just kind of naturally falls out. But perhaps the most interesting thing is what happens when we actually run it on some real data. And so this is what we got when we ran the approach on the real M87 black hole data. And what I found really encouraging is if you compare the standard deviation that we got here to the one that we had gotten earlier, you could see that there is a number of similarities, bright spots in the same similar location. And so even though these are doing different types of uncertainty, one's aleatoric versus epistemic uncertainty, they kind of come to similar conclusions of, okay, there are some areas around here that we do have more uncertainty, and that's due to basically the point spread function of our telescope array that causes that. So yeah, I was really excited when we saw this result, because it was like the very first time Ha ran the method on real data, he got the same result, or nearly the same result, that it took an entire collaboration months to achieve through those grueling parameter surveys, and it only required like an hour of training time on a single GPU. Yeah, so I'm excited to be making progress on methods like this. And as it turns out, we found that this DPI framework is not just useful for black hole imaging, but useful for many different types of problems. So here are a few that we've been using it for in our group, from seismic tomography to exoplanet orbit fitting. So hopefully maybe some of you guys might find some use of it, of something similar as well. But for now, let's get back to the black hole. So this image that we published back in 2019 was not actually one image from any one method, but actually images from different methods that were kind of all pointed in the same direction, to that asymmetric ring structure. Okay, well that process seemed to work fairly well. So now on to Sag A star. But it turns out that it wasn't that simple. So imaging Sag A star turned out to be a lot more challenging. Why? Well, even though Einstein's theory of general relativity says that these two black holes should act the same from our perspective here on Earth, they're actually very different beasts. So Sagittarius star is much closer to us. Don't be worried, it's still 27,000 light years, but much closer than the 55 million light years it takes to get to M87. And so that means that even though they're about the same size, they appear to us about the same size on the sky. If you actually factor in the distance to them and everything, that means that Sagittarius star is much, much smaller. So it's smaller than Mercury's orbit, the physical size, whereas M87 is larger than Pluto's orbit. And so remember, around these black holes, I said there's this hot turbulent gas that's spinning around, and that hot turbulent gas is spinning at about the same speed around them, close to the speed of light. But because Sagittarius star is physically smaller, that means it can make a complete orbit much faster. So here you can see these are both movies running with the same clock, and you can see Sagittarius star is orbiting really, really quickly. So gas can orbit it every 4 to 30 minutes, whereas it takes 4 to 30 days for gas to orbit the M87 black hole. And so why is this so challenging? Well, that means that as we're collecting data as the Earth is rotating, the material is swirling around that black hole so quickly that Sagittarius star's appearance is changing from minute to minute. So rather than all the measurements that we collect over a night pointing to the exact same static image in the sky, as was the case for M87, now with Sagittarius star, every measurement we take is from a different snapshot of the black hole. And so we can't just simply throw all the measurements into one pot and expect them to all point to the same picture in the sky. And so now not only do we have to deal with the sparsity and the noise, atmospheric noise, but our algorithms also have to incorporate some way to deal with time variability. And each of these decisions also is going to bias our final image. So how should we get the range of Sagittarius star appearances? Well, one way we dealt with it is by developing 4 different imaging pipelines that would survey how images would change as a function of these different imaging settings, just similar to M87. 3 of these pipelines attempted to characterize the epistemic, or what we kind of like the systematic uncertainty, like the image prior or variability model. And the 4th method had the goal, similar to DPI, of estimating the aleatoric or the uncertainty, statistical uncertainty under one kind of model. So as I said, in particular, similar to M87, these 3 surveys have different hyperparameter knobs on them, but you can see we have things like the variability model now as well included. And so from these models, we surveyed 175,000 different hyperparameter settings and saw how those imaging choices affected the images we got out. So again, we identified a collection of imaging parameters that performed well across synthetic data sets, but now these synthetic data sets had to also include some sort of idea of variability over time. And so those 175,000 different parameter settings got whittled down to about 10,000 that worked well in a series of synthetic data sets. And then from this, we could apply those 10,000 parameters to the Sagittarius star data, and this is what we saw. So we saw this huge collection of different types of images. Each of the images was consistent with the EHT data, but as you can tell, each of the images is slightly different from one another. So in order to emphasize the common features appearing in most of the images, we actually just averaged them together, all of these images together, to pull out the most common features. And from that, we got this ring image, which I showed at the beginning. But it's also important to note that not all the possible images looked alike. In fact, we found that we could cluster the recovered images into 4 different categories based on similar visual features. 3 of these categories actually contained a ring-like feature, but where the brightness around the ring changed, and there was a much, much smaller cluster of a variety of different images that did not look ring-like, and that made up a 4th cluster here. Okay, so how much smaller was it? Well, roughly 98% of the images that were produced had a ring-like feature in them, and about 2% did not. So you might say, so the vast majority were ring-like, and you might say, well, that doesn't totally rule out the possibility of non-ring, and that's true. And through many, many additional tests that I don't have time to discuss now, but I'm happy to talk about during Q&A if you're interested, that eventually led us to the following conclusion, that although we can't say anything with complete certainty, and I think science is all about error bars anyway, what we did conclude is the Event Horizon Telescope data of Sagittarius star show compelling evidence that for an image that's dominated by this bright ring of emission. And once we had felt confident with this, we moved on to interpretation, and finding that the ring that we recovered had a diameter that perfectly aligned with prior observations in theory. So two very different views of the black hole, one relying on the motion of stars that I talked about at the beginning, and one relying here on the bending and capture of light, actually were perfectly aligned, which was this extraordinary validation of general relativity. But even further than just testing general relativity, we find that by comparing this picture to simulations computational scientists have made for years, we find that it looks very similar to, very consistent with another number of these predictions. But there also were some surprises. So remember how I said our black hole was evolving over time? Well, we found that the models of the computational the models that the computational astrophysicists used were actually way more variable than what we saw. Our black hole was still definitely evolving, but not with as much ferocity as we kind of saw in the actual data that we saw in the simulations. And so to try to better understand this and understand the structures, we'd love to be able to recover the black hole's evolving structure. And to do that, so how can we do that? Well, remember I said the measurements are taken over the course of a night as the Earth is rotating. So maybe we could use those different measurements over time to recover not just a static image, but actually a movie of a black hole. So one thing you might think about doing is just break that into different chunks and image each individual chunk. But really, there's just not enough information at every time to make an image. And so we just get gibberish out. And so instead what we've done is develop methods to reconstruct full movies of the black hole evolving over time. But if you think recovering a static image is a hard to oppose problem, this ends up being orders of magnitude more challenging because you have the same amount of data, but now you have to recover all the pixels in a movie rather than as just a single image. And so to get around this, we include temporal regularization, which basically controls how similar frame to frame is, each frame in our movie is. And we can crank that up and down and see what kind of movies we can reconstruct that fit the data. And so now with this method in hand, we went to reconstruct real movies from the Sagittarius star data. But we found that when we went to make movies, depending on how much we cranked that regularization up and down, we would get different movies. And so we couldn't say with any certainty what the true dynamic structure of Sagittarius star was with the data that we have. And so as important as it is to continue pushing on the algorithmic side of using approaches like this to squeeze more out of the data, it's also important to realize that to extract more science, we also have to improve not just our algorithms, but also improve the instrument that collects the data to begin with. And to that end, we've been working on improving the actual Event Horizon Telescope Array network. In 2017, we only observed telescopes with 6 different locations around the globe. And since then, we've been building out our array, adding telescopes in Greenland, France, Arizona, and then the one I'm most excited about is here in Southern California in the Owens Valley. We're adding a telescope as well. But what could we do if we had 10 more telescopes around the globe? Well, maybe we could actually make a video of the gas slowly falling into the center of the black hole. And doing this would be a huge kind of gold mine and allow us to not just recover maybe movies, but if we had all this kind of data, maybe we could even extract more information. And so I only have a couple minutes left, but I want to highlight really briefly one last project my group is working on that I think kind of embodies this idea that I think when we work on computational methods, we should think about not just going to our science colleagues and saying, what is the science you want us to do in designing algorithms, but actually think about what our algorithms allow us to inspire new kind of scientific directions as well. And so this is one project that I think I'm really excited about, that I think kind of embodies this spirit. And there's been a lot of recent work in the computer vision community right now on doing 3D reconstruction. So we've been thinking about, well, what if we could not just reconstruct a video of a black hole, not even, we're already going from static image to video, but what if we could see the 3D structure of the hot gas spiraling around a black hole in 3 dimensions? And this imaging capability would not just tell us about the dynamics of accretion, but also could reveal the structure of space-time itself close to the black hole. But how should we go about doing that? Well, we face 2 big challenges that make it different from regular kind of 3D tomography that you might think about in like a CT scanner or something. First is that our rays are no longer straight, they're curved. But the harder problem is the fact that we're only ever going to see one single view of the black hole. We're never going to see it from many, many different angles. We're only here on Earth, right? And so that means that not only do we have gravitationally lensed 2D projections from only one orientation in the sky, but we also just have sparse measurements of that. And from that, our goal is to try to reconstruct back that evolving 3D structure here. So how can we do that? Well, by just injecting a tiny bit of the expected physics back into the problem by saying, okay, maybe we don't know anything about how the gas is moving around, but what we do believe at this point, or we'll say, okay, we'll make the assumption that we do believe general relativity. And if we allow ourselves to plug in a little bit of that physics, we can move out of that 2D plane into 3 dimensions. So this work is being led by Aviad Levis, who's a postdoc in my group, but also with collaborators Pratul at Google, Andrew at Princeton, and Ren at Berkeley. And the idea that they've come up with, I don't have time to get into details, but just to give you a rough idea, we take inspiration from very popular work in computer vision now called neural radiance fields, and we build this whole end-to-end deep learning network that allows us to solve for the 3D emission at some time 0 and an axis of rotation of the black hole. And by solving for those jointly, using the measurements from our sparse measurements from our array, we can try to recover what that 3D emission might look like. And using this network, we've shown that there's promise in using this idea to recover these like hotspot flares that would kind of that are exhibited by a Sagittarius star over short periods of time, and allow us to basically map out the space-time around the black hole. But what I find really cool about this is like, okay, well, we've plugged in some of the physics, so it's not completely agnostic to the physics, but what it is it's agnostic to what the emission looks like around it. So here you see we have these digits just spinning around the black hole. Obviously, the digits, you wouldn't expect to have these little numbers around the black hole, but we're able to recover this non-parametric kind of structure as well. So it allows us to see something kind of surprising, which we hope could enable future scientific discovery. So overall, this is super, super early stages, just a proof of concept that we're working on improving and hopefully would apply to data in the future once we have more telescope data. But I think that this work demonstrates the promising first steps of going back and forth between computational algorithms, the two-way street between computational algorithms and science. And so with that, I just want to thank the amazing team of EHT collaborators that I have the opportunity to work with on a daily basis. And in particular, I wanted to highlight Aviad, Pratul, Andrew, and Ren, who have worked on and led the projects that I talked about today from Caltech. So thanks.